Hi, my name is Ramsés Sánchez from the Lamarr Institute in Germany, and I would like to present to you some of the ideas that we have been developing to try and define novel notions of reasoning for large language models. Let me start by making 3 points. First, it is well known that large language models infer representations that encode rich semantics and syntactic content, and there have been many works showing that this is indeed the case. Second, large language models are known to struggle when dealing with tasks that require not language-specific skills, like formal and common sense reasoning. Again, examples abound. Third, there is a novel paradigm called or known as chain of thought, which prompts large language models with sequences of reasoning steps written in natural language and boosts the performance of these models when dealing with reasoning-related tasks. Again, there are many works in this direction, and recent angle is to train these models to generate themselves these reasoning steps. Key here is that this reasoning process happens in data space. We propose instead to translate the linguistic knowledge of these models onto representations that allow us to build models for reasoning. So, taking inspirations from the theory of conceptual structure of Ray Jackendorf, we seek to infer from these models relational structures that allow for compositionality. Let us then assume that there is a set of symbols encoding some high-level abstract semantic content of natural language. And let's assume that these symbols are the nodes of a hidden graph, so that connected symbols are semantically related. We then define our representations, which we name schemata, as sequences of connected symbols, which are composed by random walkers running along the graph. Then we will assume that natural language is generated conditioned on these schema representations. In practice, this means that we leverage large language model, which we modified a little to take as input these schema representations to generate sentences in natural language. Now, to infer these representations, we use a second language model to encode the sentences onto our representation space. The task is then to infer the posterior distribution over the global hidden graph and over the local random walks. So here we can see the schema distributions that we get when we encode the different subsets of the Yahoo dataset using our methodology. And in our paper, we show that the symbols that we inferred, they encode different notions of semantics. Now, with these representations at hand, we can try to tackle reasoning problems. And I will illustrate with a common sense reasoning task. So, let's assume that we are given a subject phrase like person X makes person Y some coffee, and some relation token, which in this case means what is the intent of person X. Then the task is to generate object phrases like person X wanted to be helpful. So we tackle this task in a two-step process. First, we encode the whole sentence, subject plus relation plus object, onto a random walk on our graph, so that the first half of the random walk encodes only the subject and the relation, and the second half encodes the subject, the relation, and the object. Second, we define reasoning autoregressive models, which can be a recurrent neural net or a transformer model, to generate the second half of the random walk condition on the first one. And then we can just sample novel reasoning paths to condition the decoder of the model and generate novel object phrases. So with this, with our method, we have implicitly defined reasoning as random walks on the semantic graph. And the complexity of the distribution of this schemata depends on the encoding scheme that we use. You can imagine that one can come up with different encoding schemes like the one that we presented here, and we are currently exploring different encoding schemes. So I hope that that I got your attention a little bit, and that you will read our paper and drop by our poster presentation. And thanks very much.